Hey there, Honors Bio. Happy Thursday. I know I'm in the classroom, but right now, as we speak, I'm home with my 8 and 10-year-old who don't have places to learn anymore except for home. So one day a week, I'll probably be out like this. Anyway, go ahead and grab your notes and let's talk about some stuff. Starting with a quick review. The oxygen and carbon cycle, which you knew already because of the equations that you knew. That photosynthesis is what plants do to get carbon dioxide out of the air. They also put oxygen back into the air. The carbon they take in and build into their bodies, they pass on to everybody else. Everybody else and plants do cell respiration, putting carbon dioxide back in the air, taking oxygen from the air. Then there's that below ground portion where carbon from the stuff that dies gets deposited down under the soil. It's been happening for like 3.7 billion years, and so that's a lot of carbon. Humans, though, quite recently, 100 years ago or so, have gotten real good at pulling fossil fuels, which is what a lot of that dead stuff turned into, out of the ground and putting it back in the atmosphere as CO2 and carbon monoxide. Burning wood also does a similar thing. Volcanoes are a natural way that happens, and decomposition from bacteria puts a certain amount of carbon back in the air as well. Then we cleaned up a little with, we talked about the carbon shift, how that burning of fossil fuels has shifted carbon to the atmospheric portion of the cycle much more heavily. But then we played cleanup a little bit with two concepts: the concept of niche, which is exactly how a species fits into its ecosystem, and the competitive exclusion principle, which says no two species can share a niche completely. And then we had the mosquito thing, keystone species, and how if there's a species that tons of other species depend on, they're called a keystone. That's the architectural term for this thing right here that holds the whole arch up. So if you pull them out, the whole ecosystem collapses. Good, so moving on and kind of starting chapter 4. Actually, last thing in chapter 3, chemosynthesis. I mentioned this, somebody asked, it was good when I said, where does 90%, 99% of the Earth's ecosystems get their energy ultimately? And of course, the answer is the sun. Somebody piped up and said, why'd you say 99%? What's the exception? Well, this is the exception. Chemosynthesis, which is done by some bacteria in very inhospitable places to humans, the bottom of the ocean in hot sulfur vents, the bottom of hot springs, and some swamps. There's these weird bacteria, and they turn out to be the bacteria that survived some of the early changes on Earth. These are the direct ancestors of the first organisms on Earth. We call them archaebacteria, which means old bacteria. And they are these autotrophs that don't use light to synthesize their sugars. Instead, they get their energy from the chemical bonds in mostly sulfur-containing compounds that are produced from the extreme heat from geologic activity in these hot sulfur vents and in hot springs and in some swamps. And so basically, these are the descendants of the earliest cells on Earth that when conditions on Earth went from kind of super toxic to us right now, real hot, real chemically toxic with sulfur stuff and cyanide and stuff in the atmosphere, there's a bunch of bacteria that lived in that. And then when the Earth started to change and get more like we know it now, these are the guys that survived by finding places that still look like the early Earth. So those hot sulfur vents, those hot springs are places that kind of resemble what the early Earth would have looked like. And that's how they continue to survive in those spots. Anyway, that's kind of the exception to all of our sunlight-based ecosystems. These are actually ecosystems that ultimately rely on the Earth and the sort of geologic activity of the Earth for the heat to power their chemical reactions. All right, on to chapter 4. Chapter 4, we get into sort of types of ecosystems and communities and how they function, and we get a lot into climate. Okay, we will start with ecological succession. You have seen ecological succession in action in Springboro quite a bit. One particular kind of ecological succession, which is called secondary succession. When you see secondary succession, it's when you see a place like, that corner of Austin and 741 that hasn't been developed, right? There's the side that has Austin Landing on it. Well, there's the other side that's just kind of, it was farmland at one point, and now they've just let it go. When ecological succession is what happens when an area grows from either nothing or from being cleared of something. And in this case, it's called secondary succession when you're, say, maybe farming an area and then you stop, or when there's, say, like a forest fire, we used that example, or a flood, or anything that clears the land but leaves the soil. What happens is there's a predictable series of plants and animals that move in. Mostly we track plants, right? What moves in first? Well, you can probably think of that, right? It's the same stuff you don't want in your garden or your yard. We give them a negative term. We say weeds, right? But in ecology, we give them a more positive name. So that's the kind of succession that you've seen in action. The kind you haven't seen in action, primary succession, that's the one where there's brand new land. What's an example of someplace where there would be brand new land? I think you know the Hawaii example. Have you learned about Hawaii? How there's these, it's just a perfect example of primary succession where there's these hot spots in the Earth's crust. And, as the plates kind of shift over the ocean every once in a while, one of those hot spots just kind of pukes up an island. It's crazy, like, volcanic eruption, and suddenly, oh, there's bare rock in the middle of the ocean. There's these islands. Well, somehow we got from bare rock in the middle of the ocean to Hawaii, which is like total lush rainforest in the places where we haven't developed it, right? Well, that is primary succession. Most of you have no idea what that looks like, which is okay because, and this is gonna be kind of weird, but I, a few years ago, got to go to Costa Rica. It's a story how I got there. I'll have to tell you that story at some point. It has to do with the bike rack. But anyway, I got to go to Costa Rica with some other teachers and with the author of your textbook, and with a reality show star named Hazen Audell. You can look him up. He's on a Nat Geo show. He was a genuinely weird dude. Anyway, one of the places we stopped in Costa Rica was an active volcano. And part of the course I was in Costa Rica was about how to kind of get mini lessons on film. And so I did that when I was in front of this volcano in Costa Rica, in front of a great example of primary succession. I went ahead and had somebody hold my phone and film me talking about primary succession. So I'm going to play that for you now, for what it's worth, so you can get a look at that.
Hey guys, back again in Costa Rica, out of the rainforest and into the dry forest because we gained some elevation. Behind me, see that? That is an active volcano. It's called Arenal volcano. And the rocks that you see all around here, this is a lava flow from 1992. These rocks were thrown all the way from there to here. And we're here because I want to talk to you about primary succession. We've talked secondary succession. You see old fields grow back all the time. This is what happens first. A lava flow, and then the pioneer species move in. So let's take a look. The first things, the pioneer species that tend to colonize lava first are lichens, okay? And these are the lichens here. It's a symbiotic relationship between an algae and a fungus. Then we have that followed by mosses, which you can see all around the lichens. And then some of the more adventurous plants, like the orchids you see here, and ferns, and bromeliads. So this is how an area of bare rock can turn into all the stuff you see around
you. Okay, hopefully that made sense, and the part the wind blocked out wasn't super important. Anyway, just kind of a fun thing. But so lichens, those things that move in and actually colonize bare rock. It's a fungus and an algae, and it actually knocks apart some of that rock to make it into soil or take the first steps to doing that. And then the things like the bromeliads and the ferns and the orchids and stuff is the next step. So there's always this kind of logical series of life forms that move in. Secondary succession is what we call it around here, right? When there's a farm field that then gets weeds, right? And then gets like perennial plants and then bushes and then trees, that secondary succession. In both cases, the things that move in first are what we call pioneer species. Okay, we call them weeds if they're in your garden. Give them a positive name in ecology. We call them pioneer species. They're the ones that first move in to a newly available area. So that's lichens in primary succession, and that's what we call weeds. Usually grass-type plants that when they're fertilized and they make seeds, those seeds get carried on the wind, right? They blow everywhere, and so that means they can move in fast and suck up all the nutrients and sunlight in that area and grow first. So succession, here's an example of secondary succession in an abandoned field in North Carolina. We start with annual plants, weeds, and perennials, and grasses, and then shrubs, and then quick growing trees, and then sort of the climate, what we call the climax community in some ecosystems, much like it is here, is a hardwood forest. So that is how we kick off chapter 4. Now we're going to spend a little while on climate, which I think you know what it is. Like if I were to say, boy, the climate out there today is kind of cold, I'm sure a bunch of you right away would call me on that comment and go, hey, no, that's not climate, right? What is that? That's weather, right? Climate is all about long-term average conditions in an area. It's, what's the average temperature year-round in that area? What's the average rainfall year-round in that area? What are the conditions over a long period of time in a particular area? So we'll get into more about climate tomorrow. You'll get to play Are You Smarter Than a Harvard Graduate one more time. It's a tough one, I'll warn you. But we'll start with a simple thing about climate, which is what makes our planet so special as far as climate. Like, it's in a pretty sweet spot as far as the temperatures being this kind of cozy range of, not a whole lot below 0 to not a whole lot above 100 Fahrenheit. And there's a reason for that. And it's, we're the third planet from the sun. And you might think that it's because of that nice spot, third from the sun, that we're the right temperature. It's not really. It's partly because of that. But there's nothing saying that Mars couldn't be like that or Venus couldn't be like that. The difference happens to be our atmosphere. Our atmosphere is different than Mars or Venus. And in fact, they are the two extremes on either side of us. Mars has almost no atmosphere. Venus has way too much of certain gases in its atmosphere. The no atmosphere on Mars means the temperatures when the sun's not beaten down are absolutely, kill your face cold. And the temperatures on Venus, because of so much of one particular greenhouse gas called water vapor, right, which you know well, tons, just way too much water vapor in their atmosphere, makes it absolutely melt your face hot on Venus. We're the sweet spot. And it's because of the greenhouse effect, because we have the right composition of greenhouse gases. Specifically, I bet you know, right? CO2 is one. I just told you water vapor is one. Do you know the third one? I'll give you a hint. Cow farts. Do you remember building the fart molecule in biochem? Methane, right? So here's the deal. Basically, and a great analogy here is your car. If you've ever gone into the grocery store on a hot summer day with your parents and forgot to crack the windows, and you came out, and especially if your car has a dark interior, you open the door unsuspectingly, and this huge wave of hot air melted your face. That's because visible light, if you know what wavelength is, the visible light that comes in from the sun is a fairly short wavelength, which means there's not as much distance between the peaks and troughs of the wave. And it has no problem getting from the sun, you can see my beautiful artwork here, getting from the sun, and that short wavelength radiation gets through the window of our atmospheric gases, no problem. It also gets through your car window very, very easily. But then the thing that happens is when that energy hits the Earth's surface, especially dark parts of the Earth's surface, when that radiation hits your car seats, especially dark car seats, what happens is that sunlight gets converted to heat. And heat is much different from the visible spectrum of light. We go from that visible spectrum to what we call infrared radiation. When it gets converted to heat, it becomes much longer wavelength energy. And that longer wavelength energy comes in, it came in as short wavelength energy. When it gets converted to heat, it becomes longer, and your car window really doesn't let much of it out. Like, it gets almost completely blocked because it's so long of a wavelength. The car window blocks it almost completely, and it builds up and builds up and builds up in your car to where then you open the door and, you know, it's like, you know, puppy killing temperature. The atmosphere, not quite as total of a block, right? But still, some of those molecules, some of those, shoot, where'd it go? Oh, some of that CO2, methane, and water, those molecules will, you know, when the infrared radiation hits them, they'll block it and they'll kind of direct it back downward. So just enough of that infrared radiation gets redirected and kept under the blanket of our atmosphere to keep us nice and toasty warm. Not too much like Venus, where there's so much water vapor that almost all of the heat gets trapped and it's super hot, and not so little as Mars, where too much of it escapes. And thank goodness for that greenhouse effect. That is very much what makes our planet as livable as it is. Okay, so hopefully you followed that okay, even though I didn't have a cool diagram to give you. And all right, I think that's probably good. You've got your cycle chart to work on. If you haven't finished it, go ahead and use the rest of the period on that. If there is any left, I don't know how long the quiz took you. But yeah, I'll be back tomorrow. We'll play Are You Smarter Than a Harvard Graduate? And start to look at overall sort of climate trends on the planet. Very cool stuff. All right. Hope you have a great day, and I will talk to you tomorrow. See ya.